The cable connection, I can get online and log into this thing, and it's pretty fast. All right. Okay, so this website, the first day, was created by a bunch of people at Stanford. It's a great concept, and I can tell you everything will go online in about 5 to 10 years. And for example, in many places, if you're gonna take fundamental undergraduate courses like calculus, multivariate calculus, analysis, real analysis, and so on and so forth, you will take courses from maybe the best teacher in that subject. All right, and then you probably then the local teachers, local instructors will not teach courses, but will supervise some kind of TA sessions. So it's like instructors become TAs, and TAs become free. And online teaching is the future. And lots of universities around this world is talking about online teaching. And one criticism about online teaching is the interaction. Right? You might think you don't have face-to-face contact, and you don't talk to people, and you may not learn as much, or you get bored. But it's not the case. Sometimes it can be even better if you go online. And here's an example. By the way, this is a popular website at lots of universities, especially those in the United States, are using this website to manage courses. This is the second time I use this website for my course. I did it before, and the result is really good. So I am confident that you will love it. But every group of people will have some person in the people in the group not going to want to interact with anybody. It's always like this. So I don't expect to say like 80 registration become like 80. No, it's not going to happen. But it's fine, right? But if you interact with people, you're going to find out. You learn how to become a leader, in some sense. There are like people in academia who do very good research themselves, and there are people who do good research and help others. So we want the second kind of people. Okay, so I started this note as a collaborative note, and it's called Interesting Sparse Optimization Models and Applications. These will be the topic that I'm not going to cover much in the lecture room. And so that's why I started this sequence of notes, so that you can contribute whatever you find. So when you contribute, you're going to need to summarize the interesting sparse optimization models and applications that you found from your reading. In every post, the post should be simple, and I'll give you examples. The post should give a rough background of the application of the model and the sparsity and structure that is the key to the model and the application. The most interesting stuff is here. And then give the model itself, and tell people, if you solve this model, what can you get out of the model? What kind of problem you can solve? Provide any references where you can know more about this model or this application, and also encourage you to include some illustrative pictures, or like list all the open questions. All right. So here are some examples. I created one. This is compressive sensing. This is the basic stuff of compressive sensing, which is a big topic within sparse optimization, and I would say like lots of people in different departments were very excited about this topic, and I summarize the background, the definition, sparsity, whatever. Basic things are here. All right, and then provide some illustrative examples. This is basically other people's lecture notes or papers. You can copy the link here. There are some beautiful pictures and tell you why we can compress images. This is 1.2 megabyte image. This is a 40K image. They look the same, and tell you why basically images are sparse. And then there are lecture notes and now even online tutorial, whatever. Then I'm very happy that a student from the math department, and I think she's rising senior. And she also she followed, and she says, okay, now you're talking about the dictionary model. She read about structured dictionary model, and puts her understanding here. So I came back and modified her English a little bit, but kept all the main contents. By the way, this should be main, but not in this font, but should be upright. And I think she benefits from reading and benefits from summarizing these results, and you're gonna benefit, right? And also then I responded her basically the same day, because when I wait for a bus, I wait for food, or like I'm get bored reading some paper, I come back here and put my answers here. And basically I responded her. And there are other things, like a low rank matrix completion, which is really interesting. Even more interesting topic than stars. And the interesting Netflix problem I summarized there, and give some examples. And again, she responded. The same person responded with, I didn't ask her to do this. She did it voluntarily, right? She responded with a robust principal component analysis, which is like a 3-year-old thing. Yeah. And very hot research area, and I personally know all of these, but she brought me a new application called dynamic MRI imaging. This is MRI, and except it's time dynamic. With this dynamic thing, you can use this tool to analyze basically how patient responds to some input, or like responding to heart beating or something. Okay, so I read these, and click on these papers and read those, and I get very interested in doing this. Feel free to post stuff like this. I'm gonna start new threads, and I strongly encourage you to do this. And if you register for this course, you're gonna get credit for doing this. All right. And by the way, it's very simple to do this. Let's see. Let me tell you how simple it is. Let's say I want to do low rank, and I go to edit. All right. Then this is everything. Okay. So you might be a little afraid of doing mathematics, and the mathematics is this. All right. So you're gonna need to know a little bit of LaTeX. All right. So you just put LaTeX there. It's getting embedded in the text, and it doesn't really look right because this is a little too high. But that's okay. That's okay. And everything is free, by the way. All right. So I even consider moving my research group to a post, to some kind of site here, so I can keep track of the research discussions within the students in my group. All right. So I did cancel. Back to editing. What do I want to do? A post. All right. So that becomes that. It's a great idea. So all the homework assignments and homework solutions will be posted here. So you see, there are going to be 3 homework folders, and 1 project folder, some folder called Other, and some folder called Online Seminar. And this is Online Seminar folder. We're going to do something like a seminar. Seminar means a group of people read papers and report to each other the progress. Right? So we're doing Online Seminar here. Okay, and probably I'm not going to post the homework solutions. I'll just ask the student who did the best homework and post his or her solution here. All right. And by the way, if you ask questions, you can ask here. And you don't have to release your name. You can ask the question anonymously. All right. Okay, so sign up this website. Okay, so far 17 students have signed up. I guess most of these are here, right? But I'm gonna say something. Please use your full name. You can use your Chinese full name or English. They support Chinese, by the way. So, but don't do this, because I have no idea who you are, and you have no idea. Sometimes you may have no idea, right? And don't do this. You're not Jason Bourne. Right? Okay. You know who's Jason Bourne, right? Okay. Okay. Try to use your full name. All right. So because this is we're doing real name sharing. Except asking questions, you may get embarrassed if you ask a stupid question. So you can hide your name inside that question, but when you post stuff, please use your full name and capitalize your name a little bit. All right, and please do this in about 2 days because I do cap it at 100, and I don't want this website to be like some place where people constantly coming in and leaving. So I don't want people come in and leave and constantly. So I'm probably going to close the registration by the end of Friday. So if you're really interested, please register these 2 days. And if you register, you have to register for this one. Okay. So we're going to also post some like extra material, reading materials, and extra stuff here. Okay. Now I really want to know the demography of this class. How many of you are undergraduate students? Feel free to raise your hand. You should be proud. Feel proud raising your hand because you're the younger ones. It's like 20%. Let me see. So about 15 of you, 15 or maybe 20, at most 20 of you are undergraduate students. So are you year 3 or 4? 3. Or like a rising fourth year, right? Okay. All right. So are you from math department or another department? Are you from the mathematics department or another department? Information. How about you? Who of you? You raise the hand. Someone. Okay. Basically, maybe tell me the departments. Basically tell me the background you have. No. Math. All right. Great. Huh? Computer science. Wow. Math. All right. From the other campus. Math. All right. Any other departments? No. Geoscience. Oh, okay. Geophysics. Interesting. Statistics. So the separate department. The separate major or separate department? Not separate. The same department. Same like a mathematical science school, right? Okay. All right. So. All right. So. I'm gonna need to talk to you guys. All right. So after class, don't leave too quickly. I need to talk to you guys about your background. So there are some things, if you haven't learned something, I'm gonna send you references so you can follow these courses. All right. Okay. Let's back to the lecture. By the way, I don't mean I don't care about any of the graduate students here. I really care a lot of you. Want to help you, but I usually don't worry too much about graduate students because you guys are motivated. I assume you do graduate study because you want to at least learn the latest stuff, and maybe even want to invent something new. Right? Okay. So convex set. So we're gonna encounter this, and you're gonna basically after this set of slides, you should be able to roughly recognize what set is convex and what set is not convex. So it's a convex set if it's like this. Let's say if I draw something like this, it's convex set, right? Because it means pick any points inside the set and connect them, and the whole line segment stays in the set. Okay. So, or in other words, from any point in the set, you can directly see another point. Okay. So, what is the non-convex set? The non-convex set is this. People love this, right? It's non-convex set. You put a point here, put a point here. They don't see each other. They don't directly see each other. So you draw a line section. There's some part outside the set. So this is a non-convex set. And mathematically, it's just put 2 points and connect them and see the entire line segment in the set. All right. There's some standard convex sets. The Euclidean ball is specified center. specify a diameter, a radius, and then you require all the points, center at this place and within a radius r. This is the convex set. Ellipsoid is a convex set. Polyhedron, we're gonna encounter this kind of set lots of time. Polyhedron are basically specified by linear inequality and equalities. If this set is non-empty, it's always a convex set. By the way, an empty set is also called a convex set. Alright. And there are lots of operations that preserve convexity. We call this convex calculus. What kind of operations will transform one convex function, one convex set to the other? We call it convex calculus. Now stuff like intersection. Intersecting two convex sets, intersection is convex. Now, affine function, to move things, to translate things, stretch things. They preserve convexity. Perspective function, check out the book. Right? I don't want to spend the time defining that. Also linear fractional functions. They're basically a pretty long list of operations, right, that give you convexity. Which means what? Means if you get a pretty complicated set, right, you don't have to check the definition. Or sometimes it's very, very difficult to check the definition. You might try to decompose that set into a bunch of operations, and at the end of the day it becomes a very basic convex set, like one of these three. So lots of convex sets are basic convex sets plus a bunch of operations. Right? Okay? So most of the time recognizing a convex set is not really a problem. Okay, now convex functions. We define this, but we just need to define something new. If a function is convex and it's negative, it's concave. So it doesn't curve down, it curves up, right? And if a function is strictly convex, if this inequality here, less than or equal, becomes strict. Which means it's function like this. You connect 2 points. This point, this straight line must be strictly above this curve, except at the 2 endpoints. Okay. This will be actually geometrically it is very simple, but it's going to be very useful at solving certain optimization problems. Having this property or not somehow determine whether a problem is easy to solve or not. Right. Here are some examples of convex functions. We have the affine function. You can call it linear function. Nobody's going to kill you for calling it a linear function. If we talk about mathematical in very strict sense, a linear function is this. It can't have this constant term. Once you put the constant term, we call it affine function. A constant term will shift it. Then all the norms for p greater than or equal to 1. 1 norm, 2 norm, infinity norm. But you can't go p below 1. If p goes below 1, it's no longer convex. Right? The affine functions. This is a non-trivial example of affine functions. This affine function take input like a matrix. X is a matrix, and this is a linear matrix function. Now, when I write down a linear form for matrix, there's a standard way to do that, and this is the one of standard ways. Using A transpose times X, then take the trace of this. Right. So how many of you have known trace of a matrix? The summation of the diagonals, right? Summation of the diagonals. If you do this, product, and then take the diagonal, then take their sum, it's equivalent to the summation of the product of the individual components. Right. It's just standard way of writing this. And plus the constant b. And then spectral norm. What is spectral norm? Spectral norm takes the maximum singular value of this matrix. We call spectral norm, or also called operator norm most of the time. So I do now take the singular value. By the way, this doesn't have to be a square matrix. It can be a rectangular matrix. Right? The rows doesn't have to equal to the number of columns. And take the maximum value. This is a convex function. A Euclidean norm, we're going to encounter this maybe in 2 days. Euclidean norm is an interesting norm. It's like a one norm of a matrix. So it doesn't really operate on these individual entries, but it looks at the singular values. It just takes the sum of all the singular values. It's like, it's like one norm. One norm takes the sum of the absolute values. So these are singular values. By the way, singular values are always non-negative. There's no negative singular value by definition. All right. So these are our convex functions. And there are a whole long list of convex functions. It's a whole chapter in convex optimization book. Okay, so now we do some terminology. And these terminology, some of them are not so useful. I have to be frank with you. But if you don't know them, you read papers, you read other books, you get annoyed by these concepts. So we better know it from day one. Alright, so what are these concepts? Extended value. This is an interesting thing. So basically people handle extended value is the plus infinity. Alright? So when I write a convex function like this, you can imagine, I keep writing, At every point it's well defined. You give me an x, I'll return you a value. But now this value allowed to be plus infinity. Alright? So that's called extended value. So what kind of functions have extended value? So if I define a set D is a convex set. Right? And then I define a function so that when you're staying inside the set, it gets 0. When you leave the set, it gets plus infinity. Right? So I define function f of x, which some people write it. This is iota or c. People do this iota d of x, which basically means that. By the way, this has to be closed. Okay. So basically the boundary are included. Then I write it's 0 if your x is inside the set, and plus infinity if x is outside the set. Right. This is extended value convex function. Right. Proper means there exists at least one point this function is finite. It's not always plus infinity. And there's something more subtle. It's called lower semi-continuous. Lower semi-continuous deal with this kind of thing. So I have an extended value convex function, and here it has finite value, but starting this point to the left, it has plus infinity value. It's plus infinity. Alright? So this is a convex function. Now, for this breakpoint y, I can let this breakpoint, put this breakpoint here. So in other words, if you are at y, you have finite value. Or I can put this point to the plus infinity side, and this is empty. In other words, at y you have plus infinity. Right? A lower semi-continuous means this point is actually finite. It has to be finite. Whereas the end point, the plus infinity, is not inclusive. It basically says this. So why do we need this? Because sometimes you may get a solution here. Right? Sometimes you do minimization, you want to get a solution here. If this point is actually plus infinity, you may not have a solution. You can get arbitrarily close to this point, but you can't get to this point if it's over there. Right? So lower semi-continuous means, take the lim inf, you get the finite value. And it is equivalent to say closed. Closed means the so-called epigraph of this function is a closed set. So epigraph is basically the point, the input point, and the value itself that are above the function. So this is the 1D function, right? This is the 1D function. What is the epigraph of this function? Epigraph of this function, this is empty, right? This is empty. Epigraph of this function is this set, and this is 2D set, right? Extended. This is the epigraph. If my value at y is finite, then I'm gonna get a closed set because this piece of boundary is included. if this value is infinite, then I won't get this piece of boundary, and therefore this set won't be closed. So therefore, whenever we talk about a proper function, the function is closed if and only if it's lower semi-continuous. It basically tells you very little information, but if you read papers written by Russian, written by say French, they can always put these things in. Right? They like showing off their like rigorousness. So we also what's interesting is especially in sparse optimization, lots of time I'm going to deal with non-differentiable functions. We're going to deal with convex but non-differentiable functions, like the absolute value function. Like this kind of function. This is a convex function, right? But it's non-convex at this point. But we still have to use this subdifferential to do algorithms to say something about optimality of the function. So subdifferential is going to be used a lot to derive complexity bounds. Now, at a point where the function is not differentiable but convex, you can define something called subdifferential. Subdifferential is basically the slope of the support line. So a line supported means I have a line that's below this function but touches this function at some point. It means this line supports holds this original function, right? And the slope of this function, you can see that the slope of this function can change. It can go from -1 to 1. And that entire set, in this case the -1 to 1, this entire set is called subdifferential. And subdifferential is mathematically defined this way. If you are subdifferential P, and I compare two values, I compare the original function value and compare the so-called linearization along this direction. So this is f of y, let's say, and this is f of 0 plus the subgradient p times y. Right? I just say that the entire line must be below the original function, below or on the original function. Therefore, this defines the subgradient. So this is the definition of subdifferential. If the function is, by the way, subdifferential is always the set. The set of vectors is not a single point. Even if your function is differentiable, subdifferential is just a singleton, a single point set. Alright, so next topic, it's a very important topic called first order optimality condition. What is that? So when we do optimization, the first thing we think about usually is not the method to solve the problem. If you're an engineer, you're given a problem, and then the first thing is how do I solve the problem? But in optimization, the first thing we do is not to solve the problem, but to tell if a point is optimal or not. Right? So even if I give you a point, can you tell this point is optimal? We need some conditions that test this, and these are the methods of testing these optimality. This is one of the conditions called first order condition. First order condition means that you use the first order derivatives. Use the first derivative of these functions. If this function is convex and differentiable, then you take the gradient. By the way, gradient is column vector. When we take gradient, it's column vector, so that's why I write a row vector and take a transpose. And also, by the way, say these are both letters, these are vectors, and these are individual components, which are non-bold. This is the standard math fonts. Right. So a first order condition, a differentiable convex function. This is a condition that testifies this function is indeed convex. So I've already told you the definition of convex function. I'm using 2 points and connect the 2 points and compare, right? But if this function is differentiable, there's another way to say this function is convex or not, which uses this inequality. Okay? It basically says that the function should be always above its linearization. So the so-called linearization is the following: you fix a point and take the gradient, take the tangent of this function, and then connect the tangent, extend the tangent at the line. So this is called linearization. It says the function should always on or above the linearization at any point. If a function has this property, then this function has to be convex. Yeah. And this is the if and only if condition. Alright? So which basically means if your convex function is differentiable, things become easier. You can use the gradient to simplify the condition. Alright? And then this is the first order condition for non-differentiable but sub-differentiable functions. If you take sub-differential, so you're going to replace the gradient by just all set of sub-differentials. You can't just use one, you have to be all. Alright? Now, and this is the condition I talked about, the first order optimality condition. If you minimize, you want to minimize a function without any constraints, and this function is convex and differentiable, there's a simple way to tell you're already at a solution or not. So X is the argument means the set of minimizers. The X star is one of those points that minimizes this function if and only if you look at the gradient or subgradient, 0 is there, which basically means you have a function like this, and you're there. How do you tell it's global minimizer? You just look at the tangent. The tangent is flat. You have to be the minimizer because you know all the other parts are going to curve up. Okay. And it's also true here. Even if you have extended thing, extended thing here, you're going to have a bunch of subgradients. This is the gradient. This is a subgradient. This will be a subgradient. This will be a subgradient, etc. But the flat bar has to be one of them. If this point is the global minimizer. So which it's really simple, right? Just calculate gradient. Now, second order condition. If your function is also second order differentiable, you can define something called Hessian. The Hessian is a matrix. The ijth component is the function first. Oh, by the way, this should be really bold. I made a mistake. This should be bold. So first take derivative with xi, then derivative with xj. Now, second order condition says if a function is convex, then the Hessian matrix is always positive semi-definite. Good. Do you want me to repeat the definition of positive semi-definiteness? So, do you know what this means? Right. It means the following. It means. I'll first tell you the definition and then tell you the geometry. Well, a matrix H is positive semi-definite, and if X transpose H, X greater than or equal to 0 for just any X. Which basically means, this is the quadratic function, right? This is a quadratic function. It basically means the quadratic function like a bow. And this also means that at this point X, the curvature is curve up. You leave the point, you're going to go up at every point. Right. So this kind of thing, at every point you're going to actually have H strictly positive, which means this inequality is going to go strict if for any X non-zero. Now, if you have some flat part, and so here you're going to have H actually equals 0, and there's no curvature. So this thing is really just the curvature. How much curvature we have on the function. So if this curvature is always 0, it's either flat or you're going to go up, curve up, then it must be a convex function. It's geometrically it's very clear. If you're talking about strictly convex function and twice-ly differentiable, then it has to be strictly curve up. Okay. All right, second order differentiable. And this is the definition of convex formulation. There's another way of defining convex optimization. You have seen this before. And the way is, what is a convex program? A convex program should have a convex objective so that all the point x, all the feasible points x can stay in the convex set. So basically these inequality and these equality constraints, they together define a set of points that are feasible, and the set is convex. Okay? Alright. Now this is by far the most important thing about a convex programming. It's just one simple algorithm, one simple theorem, and it's embarrassingly easy to prove. It says any local solution, so whatever solution you find, that's best among the neighborhood, is also a global solution. So local means global, and by the way, it's easy to find a local solution. Therefore, for convex optimization, it's easy to find a global solution. The proof is following. So let's suppose X is a local solution, Y is a global solution. Now it means Y is really much better than X. Right? I wouldn't say much better, but Y gives you a smaller objective than X. X may be best, but only best in a small neighborhood. But Y is the global solution. All right. And then you're going to use the convexity of the function and convexity of the set. You connect X and Y, you get Z, right? You get Z. And because the feasibility set is convex, so Z is feasible. In other words, Z satisfies all the constraints. So then we can just purely compare the objective values. Well, it says the following. Well, Fz, use the convexity of this objective function. Fz going to be less than or equal to a weighted sum of the objective values at f of x and f of y. Now, f of x is larger, f of y is smaller. Therefore, this is going to be less than f of x. Okay? So in other words, for any theta, or actually I should say, we're taking a theta between 0 and 1. For any theta between 0 and 1, you're going to get a point that's strictly better than x. Z is strictly better than x. But, because theta can be any point here, you can pick theta near 1, like a 0.999. You can get this theta really near 1, and then this point Z will be very close to x. So in fact, by picking a property theta, Z can be arbitrarily close to x. So no matter how close you can get to x, you always find a point that's better than x. So x cannot be a local minimizer. This is a proof by contradiction. It's a very simple proof by contradiction. So this is saying the distance can be arbitrarily small, so x cannot be a local minimizer. It cannot be just the best among the neighborhood. It has to be globally best. So any local solution is a global solution. So by the way, in most classes I won't do too much detailed proof, and I'll only do like proof concepts or fundamental proofs. Okay. Optimality criteria for differentiable f of x. So we have seen this. Basically, if f is differentiable, this thing should be 0. This gradient should be 0. And if the feasible set is okay. I think I should say now here I consider there's a feasible set. This is a constraint optimization. So X is globally optimal if and only if it's, of course, they have to be feasible, have to satisfy all the constraints, and this inequality have to satisfy at X, but for all Y, all points that's feasible. So here, this is what it means. So suppose I draw a graph like this. So this is plus infinity, and then it's lower semi-continuous. Okay, sorry. Let me draw a different graph. I think 1D is probably not enough. Let me draw a two-dimensional functions. So let me draw two-dimensional functions, and I'm gonna do the following. So I'm gonna draw level sets. All right. So this is the quadratic. This is a bunch of ellipsoids. So the solution is obviously there. The minimum solution is obviously there. So So this is the level curves of f0 of x, and that's the global solution. This is unconstrained case. Now, if I impose constraints, let's say I have to stay in this area. I impose constraints. Now, this point becomes infeasible. I have to eliminate this point. It is not qualified. I have to stay here. And then, what is the minimal solution? Well, you can probably see it here, right? Because this is the point where I tangent to a minimal level curve possible. Right? It's here. If I go to any other point in this feasible region, I'm gonna definitely be on some curve that's higher. So this is the minimal point. Now, how do I tell this minimal point? Now, this function is differentiable, right? The derivative of this function goes here. This is the derivative of that function. Right? Derivative basically is the direction that you're going to get maximum increase. Fastest the speed increase. That's the derivative direction. It tells you this is the derivative direction. So this is f. And if this point is x bar, this is the gradient f0 of x bar. All right. And this says, if you pick any point in the feasible region, let's say this point y, and then connect this two points, and this is y minus x. Y minus x should make a small angle. So should make an angle less than 90 degrees with this gradient. And if this is true for all y, then this point is optimal. All right. So this is another way of using gradient to tell whether a point is optimal, even if you have a constraint set. Which basically tells you the level curve of the objective function should be tangent. Should be tangent to the should be perpendicular to the boundary. Should be exactly perpendicular. It has to be 90 degrees. If it's not, if it goes down like this, then you should be able to go that way to decrease your objective value along the boundary, right? So it really just means so the gradient should be tangent should be orthogonal to the boundary tangent and make a smaller angle with the points. All right. So there are some applications. If there's no feasible set, y is everything. Therefore, the gradient has to be 0. And if this feasible set is a linear function, linear functions are hyperplanes. So I really covered too much in one lecture. If you're undergraduate, you haven't touched this stuff. That's really a lot. So I'm looking at all the points that satisfy a bunch of equations. I suppose this equation has a solution. Now, what is this? This is called a hyperplane. People call it hyperplane. So it's some kind of flat surface in a high-dimensional space, right? The key thing is flat. It's like a plane, except it could lie in the high-dimensional space. Now, you can think it. You can imagine it. It's something like this. Right? If this is the feasible set, if you have to stand here and look for a point that's minimize the function, then at the minimum solution, at the minimizer x, your function should have a gradient that's perpendicular. It's either go up, perpendicular to the surface of the plane. Otherwise, if it's not perpendicular, you can always move along some direction and improve it. So this is what it says. So the gradient should be a linear expression of the normal directions of the surface. So this A, so if I write it like this, and I write A as a bunch of row vectors, the row vectors. But what are these row vectors? All of these row vectors actually are perpendicular to the surface, and these are called normal directions. So my gradient should be also normal to the surface. Therefore, it's a linear combination of the normal directions of the surface. So, I mean, it's a little hard to, if you have touched this, if you have ever thought about this, I say this, you understand. If you never touched this, never seen this before, it's a little too fast. I understand that. But you have to go back to the textbook. Here's another example. If I minimize the function over the first orthant, the part of the Euclidean space with all the components non-negative is called the first orthant. If I minimize the function within the first orthant, then this point will be optimal if and only if the following conditions are satisfied. I'm going to need to look at whether this number is 0 or strictly positive. When you are 0, you're actually at a piece of boundary. When you are greater than 0, you're away from the boundary. Right? When you're at boundary, you're gonna use just use something like here, like this. And if you're away from the boundary, the component have to be 0. All right. So I leave yourself to figure out the geometry. Okay. So I think once you figure out this one, and all of these above are simple. And once you figure out these one, you can actually deal with more complicated sets than this. Okay, unconstrained problem with non-differentiable f of 0f. With non-differentiable objective function. Okay, I think I'm going to skip this. I do want to eat lunch, so I skip this. But please take a look. All right. So I'm gonna start doing with the more general case. So this is the one of the most general optimization problems with all the inequality and equality constraints. Now I only know it's and it may not even be convex. I only know it has let's say okay, I don't even assume, for the moment I don't even assume it's differentiable. It's one of the most general problems. So you minimize a function subject to a bunch of inequality functions and constraints defined by inequality functions and equality functions. All right. So to tell the optimality of this, there are some standard approach. The approach I use is something called Lagrange. It's actually a generalization of the geometry that I just described. It's something like this. It's just a fancy generalization of this. So let's see how to do it. You do it the following. The Lagrange has 3 kinds of variables: the original variable and 2 kinds of variables called Lagrange multipliers. It's probably like some section in your mathematical analysis textbook. And so the so-called Lagrange is basically a original function plus the linearization of the violation of the constraints. So this is how it reads. So fi of x should be less than or equal to 0 if it's feasible. But you allow f of x to be actually greater than 0. You don't care about whether this value is less than or greater than or equal to 0. But whenever it's greater than or equal to 0, you're going to assign a price, lambda I. So if it's greater than or equal to 0, it'll incur an additional cost to the objective function. And same thing here. If hj is away from 0, you're going to incur a cost. So the key thing is you forget about the constraints, you allow them to be violated, and when they are violated, you're going to incur an additional cost to the objective function. It's called Lagrange. Now, so what can I say about this Lagrange? There's a very interesting property. Now, if I require lambda to be greater than or equal to 0, I mean this is component greater than or equal to 0, right? If I allow lambda to be greater than or equal to 0 and allow nu to be anything, then you minimize this unconstrained function. Forget about any constraints. Forget about the constraints that used to be there. Now, if they were feasible, if this point were feasible, this is greater than or equal to 0, this is less than or equal to 0, so this term will be less than or equal to 0 altogether. And this term, if x is feasible, this term will be 0, so this term will go away. So you were going to just minimize the original objective. That's fine. That's exactly equivalent to the original problem. But now you actually don't impose those conditions. When you relax the conditions and you do a minimization, you should get something even lower, right? So if you fix the price variable, it's minimized over x. By the way, this should be both x. I made another mistake here. And this value should always be less than or equal to the original optimal objective. The P star is the optimal objective of the original problem. Therefore, you get a lower bound. Right? This doesn't really, there's nothing deep here. It's almost trivial, but this is very useful because the original problem might be very difficult to solve, but this problem can be sometimes trivial to solve. And believe it or not, this thing has actually applications in distributed, large-scale big data optimization, in network, in clusters. Right? Some ideas are actually based on this relaxation. So there's an interesting lower bound property. So when I talk about lower bound properties later, you can look up some chapter 4 of the convex optimization textbook. It's going to tell you when this thing can be equality. It's important it become equality, which means you almost solve the original problem. Under some conditions, you can choose lambda anew such that this is equality. Okay. So now the problem of By the way, you have freedom to choose lambda mu as long as lambda is greater than or equal to 0. Right? As long as lambda is greater than or equal to 0, you have freedom to choose lambda nu. Different lambda nu are going to give you a different lower bound. But this is the fixed value you want to recover. Therefore, you want to maximize this quantity. The maximization of that quantity is called the dual problem, or Lagrange dual problem. Right? But most of the time, you see a dual problem in the paper, in the textbook. It doesn't look like this simple, because G usually has a rather complicated forms. Right? G has a complicated form. But this is the abstract way of writing the dual problem. The goal of dual problem is to find try to find maybe the best lower bound on maybe off of P star. Then it's also a convex problem because you can show that this thing is always a convex function, even if the primal problem is not convex. This dual problem is always convex. All right. There's another good thing about Lagrangian dual. And there are some conditions that will give you strong duality. The optimal objective of this guy is going to equal to the optimal objective of the original problem. Right? There are some conditions, and basically, it does not always hold, but usually hold for convex problems. For non-convex problem, it doesn't hold like 99% of the time. There are like exceptions, which people care about. But for convex problems, most of the time it holds. Does not always hold. You need extra condition called a Slater's condition. All right? The condition guarantee this thing for convex programs are called constraint quantifications, basically. Now, I'll give you just one condition quantification coming up by a guy called Slater. It says the following: if you have a convex program like this, right, you wonder when this primal dual duality, the primal dual actually meet. Which means you can solve basically one problem, you can automatically solve the other. The condition is this. So this inequality constraints can be made strictly feasible. When I say strictly, it means that I can find a point such that all the inequality constraints hold with strictly inequality. It's a very simple condition. And this is a sufficient condition, but not necessary. But this is a condition that's easy to use. All right. We're about like 10 minutes from the class is over, so I'm gonna leave these to you. Right? These points to you. And I skip complementarity. I'm gonna do it maybe in about 2 lectures. This is also important stuff. The final most important thing is called the Crush-Kuhn-Tucker conditions. These KKT conditions of the most general. Why does this classroom suddenly become so quiet? It turned off. Okay. Well, so let me try to finish this thing quick. The KKT conditions of a of a constraint optimization is really like this. It's just generalization of what I draw. It says the following. It has the following parts. It has like 4 parts. The first part is you have to be primal feasible. You have to satisfy all the constraints in the primal problem. How do we guarantee this? Just check them. Just check them. Right? What's difficult to check is the optimality. It's easy to check whether a point is feasible. Just plug in the number to the functions. Right? And they also have to be dual feasible. You have to, for this inequality constraint, the dual variables have to be dual. Lagrange multipliers have to be non-negative. Then they satisfy the complementarity slackness, which I skipped, which basically means these two guys cannot be strict at the same time. At least one of them have to be 0. For every inequality constraint like this, I'm gonna have a lambda I. That lambda I, if that lambda I is greater than 0 strictly, then the corresponding fi of x will be 0. So at least one of them is 0. It's called strict complementarity. They have to be satisfied. If this is not satisfied, there's going to be a gap. There's going to be a gap that cannot guarantee the optimality. And then finally, it concerns optimality. Concerns this. It's basically the gradients. The gradients should be some kind of linear combinations of the. By the way, these are the boundary gradients. So if I can't have a constraint set like this is a set of constraints, and then I have a bunch of level curves of the function I want to minimize, right? And these things are just the outward gradients of the boundaries of the constraint boundary. So these are outward gradients of the constraint boundary. Outward, this have to go outward, this have to go outward. So that's why this lambda I have to be non-negative. This doesn't matter. This is equality constraint. It's a flat surface. So this new j can be anything. But the gradients of the objective have to be a linear combination of the gradients of the boundary. This is the KKT conditions. I do prepare 2 exercises for this lecture, but I think without the L conditioning, you probably don't have the mood to do it. No. So I prepared 2 slides of exercise, and that's the end of the lecture. So I leave them to you. And also, so the first thing you do is after lunch, whenever you have internet, register piazza.com. We're gonna post homework assignments on piazza.com. All right. Okay, and let me know if you have any concerns and comments, or the coverage or anything about this course. Let me know. Okay. All right. So that's for today. I'll see you tomorrow at 9 o'clock.